clear? So let us proceed from here on. So we are going to be looking at distributors fed from both ends. Okay. So we are going to be looking at distributors fed from both ends. Now these ones here, they're simply in this book here. Let me share with you. They're simply in this book here called DC Distributors. But you see, as simply as what we had earlier on studied, we had introduced the distributors, the types of DC distributors, and we said we have one fed at one end, we have one fed at both ends, we have one fed at the center, and then we have the ring distributor. So from that, we went earlier on and tackled the distributors fed from one end, and I gave you a basic example. So let us look at the calculations concerning distributors fed from both ends. So calculations are here simply. There are lots of examples, but let me rush down to the ones for distributors fed from both ends. Sorry. Okay. This is a uniformly distributed, uniformly loaded distributor. So here we have the distributors fed at both ends. Now they can also be categorized into two. We have one which is fed from both ends but with uniformly distributed loads. Then we have one fed from both ends with the concentrated loads. So this one, the basic one we shall look at is the one fed from both ends but with concentrated loads. If I can maybe have my book, there is that particular example which he did last weekend, and it's what I wanted to go through. But briefly, let me do an introductory, let me do some introductory part about it, then we can be able to see how we shall be tackling such a number. So when you have a distributor that is fed from both ends, it is just simply having a distributor, maybe A to point B. Now people who are online here, please mute your microphone. So we have a distributor running from point A to point B, and then it has a feeder. Now we shall have feeders at both ends of the line. We shall have a feeder at this point and also a feeder at this point. Then we shall keep on tapping on concentrated loads along the entire section of the line. So for example, along this section, we can have points maybe C, D, and E. Now along those sections is where we are going to tap off our loads. Let us give them values, such as maybe, let us give them this one to be, let us call this one a certain current, I1, I2, and I3, as shown. So what we are going to do with such a kind of a distributor is that, first of all, we need to know the area, the place where we have minimum potential. And to be able to calculate that, we need to first of all get the currents flowing in each section. So I was saying that to calculate for those, we need to get the point of minimum potential, and we shall do that by getting to find out the potential at each particular. Okay, to find the potential at each particular section, we first of all need to get the currents. We shall first get the current flowing through this section, this one, and that point. Then we shall keep on subtracting, we shall get the voltage drops, and then we shall be able to calculate for the voltages at these points. So from this, we don't know, since there is current coming from this and there is current coming from this side. Okay? What we do is we shall assume to take one of these two sides, and then we assume a certain current, maybe Ix. Now for me, I prefer to work from this side. So I will have a certain current Ix, and along this particular section of the line, I will be having different values of current. Suppose this is Ix, there is going to be a current flowing in this and this particular section. Now, when it reaches that particular point, we shall need to first of all get, if we want to get the current flowing here, it will be equals to, using KCL, shall use the current entering equals to sum of currents leaving. So here the current entering is 1, but the currents leaving are these 2. So meaning the current in this section will be simply this minus this. So here the current flowing in this section will be Ix minus I1. So similarly, we shall do the same now. I don't know, there's an issue with my pixels. Just a moment, let us first sort something so that you don't strain your eyes a lot. But is the image clear for you here? Or we need to a little bit compress it? It is fine, eh? It's not the light, not the problem. Problem is just a moment. Please, we have overzoomed again. It needs to be somewhere around here. Yes. You still get there. Then the ruler. Okay. Let them ruin it. Okay, that is going to be sorted a little bit for the people who are online. At the moment, let us keep on proceeding. At the moment, let us be proceeding as we work on the image quality. Now, the issue is we are not in our production room. This is an outdoor setting and it was so random, we're not so much ready for it. So, at the moment you bear, but we shall work upon that. Similarly, to get the current flowing in this section, it's simply going to be equals to, we shall get this previous current, for example, the previous current minus this I2, so here it will be Ix minus I1 minus I2. Okay? Then similarly, we shall have also current flowing in this section will simply be, what did you do?
If you can make one or two big overarching analogies for the most important concepts or group of concepts, or the
So from that particular section also the current will be simply, we shall get these previous currents and then subtract I3 from them. So it will be Ix minus I1 minus I2 minus I3. So just simply like that, we shall be able to calculate the currents flowing in each particular section. Then the part of getting the resistance across each section, that one I won't re-explain it because we have done it previously. So with that, you're going to allow me to look at a particular number. Maybe we can select an example and we see how we can do this. So this is just basically it. Maybe another thing to explain is when we have current coming from this side, and we have also current coming from this side, there is going to reach a point whereby these currents are going to do what? Meet. And when there is that point whereby their currents are meeting, or what he prefers to call it is when there is a change in direction of the current, that point qualifies to be called what we call the point of minimum potential. So for example, in this section here, our current IE, at the point point E where the currents are changing direction from this direction to this direction, is our point of minimum potential, just as Mr. Beru had clarified on earlier on. So those ones there, it is just briefly a preview of what we had done. Now, maybe furthermore to explain a little bit, is that when we have our voltages between this point A and point B, okay, they will give point A a certain potential, maybe VA, and they will give VB also a certain potential, let's say VB. So when we have these potentials VA and VB, a point is going to be reached whereby we shall have to get the first of all to calculate for the, after getting our resistances per section, let's say this resistance is called RAC, this resistance is called RCD, RDE, and REB respectively. So a point is going to be reached where we shall need to get the total voltage drop across this in order to calculate for Ix, the unknown current we have introduced. So to get the unknown current Ix that we have introduced, we shall say maybe voltage now you know the sum of voltage drops, the rule is the same. So we shall use that to get VA is going to be equals to the sum of individual drops along this point plus the voltage at the other end. So it will be equals to VB plus now the current flowing through this times the resistance there. So it will be Ix times RSC plus the current flowing in this section times the resistance there. So it will be, now the current is Ix minus I1, okay? And then the resistance across this section is RCD. So simply you will keep on calculating for this, for the entire section of the line. And at the end of the day, VA is given, VB is given. You have all respective values of R. So you can take VA and VB the other side. So you have VA minus VB being equals to, so you have VA minus VB being equal to the sum of these values here. So you will get an individual value of Ix times a number RSC plus all the rest of these. So at the end of the day, you can make Ix the subject since you've calculated for the all respective values of Rs, and the currents here will be always given in terms of amperes, maybe 30, 20, and so on and so forth. So you find that what you're going to be left with is simply making Ix the subject. I don't know if we should review maybe one particular example before we go to the one that the lecturer had given us last time. So I'm going to take us through one example here. Maybe we see how it's done. Let me look for a worked example. And yes, we can do this worked example over here. Now, as you're reading through, let me do some adjustments on the okay, if it is okay, then we can use it. So here we have a question. We're having it. I think this is what we did last time. Let me go to another example down here maybe to change, because this one here we did it last time. Let me look for another example here and maybe we can work that out. So we're having example 13.11. It's saying a two-wire distributor. Let me see what they want. Yes. So let us work out with this. They're saying a two-wire distributor, AB, is fed from both ends. At feeding point A, the voltage is maintained at 230 volts, and at B, the voltage is at 235 volts. The total length of the distributor is 200 meters, and the loads are tapped off at as shown as below. So 25 amps at 50 meters from point A. So they are measuring from point A, 30 amps at 100 meters from point A, and so on and so forth. So let me give this on different, so that we can start afresh and calculate for this. So we are going to draw an equivalent diagram for this. So here we have our example. They are saying a two-wire distributor AB is fed from both ends. At feeding point A, the voltage is maintained at that. So we have a distributor AB as shown below. So this is our distributor from point A to point B. So this is point A, this is point B, and here we have our feeder, and also here we have our feeder. Just a moment. Okay. So we have our distributor AB as shown there, and it is having feeders at point A and point B. Now at point A, they are telling us the potential at point A is maintained at 230 volts. So here, sorry, my screen has frozen. Okay. Just a moment. Sorry. Yes. Okay. So let's proceed from there. So we're looking at this. So we're looking at this particular example, and we're considering the given parameters. So they have told us, now here they have given us the loads. They're telling us the loads are being tapped at those particular points from end A and point from end B. So before I went through that, I was saying that the voltage given at point A was given to be 230 volts. So V at A is equals to 230 volts. And then the voltage at point B was given to be 235 volts. So the voltage here is 235 volts. Now, along this length of the conductor, they are going to tap off loads. They are having 4 loads. That is load 1, load 2, load 3, and finally load 4. So they are giving us that the first load is 25 amps at 50 meters from point A. So this is our 25 ampere load. Then here we shall have our second load, which is 30 amps at 100 meters from that. So this is 30 amps. Then, sorry, no, it's not the second one. It is 75 first, according to the question. According to the question layout, they are giving us this 25 at this. Then they are giving us 50 amps at 75 meters from point A. So we shall have our 50 amps here at 75 meters from point A. Now it's best to keep on integrating these lengths as we are working out. So for example, the first length was given to be 50 meters from this point. So this is 50 meters. Then the second load was given to be at 75 meters from point A. So it will be 75 minus 50 to give us a 25. So this is 25 meters. Then similarly, we have another load at this point, and they're telling us this is a 30 amps load, and it is at a point 100 meters from the other end. So 100 meters is from point A. From here to here is 100. That means from here to here is 100 minus 75, which is going to give us also 25. Then we have the last load, which is 40 amps at a distance of 150 meters from A. So if this is 150, but from here to here is 100, so the remaining distance there is 50 meters. So we shall have our 50 meters here. And finally, did they give us the total length of the line? They didn't give us yes, they told us the distributor is 200 meters. They told us the distributor is 200 meters long, and our last point is at 150 meters. So you can see clearly that the remaining distance will simply be 200 minus 150 to give us this 50 meters. So our last point there will be at the section there will be 50 meters. Now, from that point there, we need to calculate for the various values of current flowing in each section. So how do we do that? To calculate for the currents, we shall first of all, let us name these points here. We can name this point to be, so we can have this to be W, X, Y, Z, like that. Now we can have currents flowing in these particular sections. From any direction, you can choose to work from A towards B, you can choose to work from B towards A. Now if I assume this unknown current to be a certain value, maybe I call it I what? We can call it source current IS. So the current flowing here will be simply source current minus the current that has been tapped off. So this will be IS minus 25. Then when we reach this point also, the current will be this current here, which is IS minus 25, minus this 50, which is being tapped off. So it will be IS minus 25 minus 50. That is giving us IS minus 75. So similarly, from here to get the current flowing here will be simply this current here minus what is being tapped off. So that will give us IS minus 105. Then similarly, this last current will be this minus 40, which will give us, let me write it down here, to be my IS minus 105. Okay, 145. Thank you. So this is IS minus 145. Okay. So let's move on from that point. We need to calculate now. We know the currents flowing in each particular section, even though they are in terms of unknowns. Now the next step is always to find out the resistances of each section. So how do we do that? We go back to the provided information and see what we are given. So they are giving us that the total length of the distributor is that, and it is having loads at that particular point. Now they have not given us the what? Yes, they are saying the resistance per kilometer of one conductor is 0.3 ohms. So they want us to calculate the current in each particular section and the minimum voltage and the point at which it occurs. So, step number one of coming up with our diagram, you can see it is identical. We have done it. Now let us go to step number 2 of finding the resistances of each section. So now here, what they have given us is the resistance to be 0.3 ohms per kilometer of one conductor. But remember, we are dealing with a two-wire DC distributor. So this resistance shall be converted to that of the two conductors. So they told us that resistance, yes, of one conductor was equals to 0.3 ohm. It was resistance per kilometer, per K meter. So they want us to calculate. So from here, we know the resistance of one conductor per kilometer. So the resistance between the sections, for example, the resistance R between section A and W is going to be simply equal to, we shall get the resistance per conductor and we multiply it by 2 because we are dealing with 2 wire. So it will be 2 times the resistance per conductor, which is 0.3, then divide by the length of the per kilometer. Per kilometer, that is meaning per 1,000 meters. So we change it to meters and it will be over 1,000. Okay? Then we shall multiply it by the length between A and W, which is 50 meters, as we had earlier on calculated. So it will be times 50. So someone with the calculator, help us with the answer here. So from that, let us find the final answer there. What is the answer? It is 0.03 ohms. Those who are online, you can also feel free to participate in getting the final values. So that is the resistance between A and W. Let us find between W and X. So similarly, we shall do the same thing. Resistance between W and X will be equals to 2 times the resistance per conductor, which is 0.3 over 1,000, times the length we have between W and X, which is 25. So I believe this will be just a half of that value there. And that will give us, 2 times that will give us 0.15, is it? 0.015. Yes, 0.015 ohms. So similarly, you can get, you see, now these ones are the same because the distances are the same, 50, 25, 25, 50, 50. So I'm going to expect to be, the resistance of here is this. The resistance of between this section is what we have calculated later. So the resistance between this is going to be the same as this. Then for these ones, they're going to be equal because the lengths are the same. Okay? But for the sake of time, I'm not going to calculate them. But in case you wish to calculate them, you can still write the same formula. So here, the value of resistance between section X and Y is also going to be equal to 0.015 ohms. And then the value of resistance between Y and Z is also going to be equals to the previous value of resistance, which was 0.03 ohms. And finally, the resistance between Z and B is going to be equals to also 0.03 ohms. We're together up to there. You can feel free to ask questions. So, proceeding on from that point, we are going to calculate for the value of IA, which is the unknown current. Now, to calculate for the value of IA, the unknown current, shall simply go back to we shall be like we're calculating the total voltage drop along this section. So, using that diagram and referring to what we had earlier on, the values we had earlier on got, we are going to say, therefore, that the value of the value of voltage at point A, like the way we had done earlier on, if you want to get the voltage at point A, is going to be equals to the sum of photovoltage drops along this line plus the voltage at the other end, not so? So this is going to be equals to 50, because it's the current flowing here, times the resistance between this section, which is R, AW, plus, was this 50? No, it was IS, sorry. This 50 was the distance, okay? So we shall say VA is going to be equals to our IS times the value of resistance between there, which is RAW, plus this value of current flowing there, which is IS, minus 25, times the resistance across that section, which is RWX, plus our current flowing through that section, which is IS, minus 75, then times the value of resistance across that section. The resistance across that section is RXY. Then similarly, it will be plus this last section, which is having, though it's not the last section, it is IS minus 105. So it is IS minus 105 times the resistance across that section, which is RYZ, plus also the last section, the current flowing there is IS, the value of current flowing there is IS minus 145. So plus IS minus 145 times the value of resistance across that section, which is RZB. So these values here that we are having, we have calculated all of them. Now I have not added plus VB, okay? So there is a plus VB this side, which is given the voltage at this point here, VB. So from that, the values that we have, we can take VB and VA the other side, since we already have them. And then we shall keep on substituting for the values of RA, RX, that, and all these other respective values, such that we shall remain with only IS as the unknown in this equation. So at this point, we shall have VA minus VB being equals to IS times R A1. Now, referring to what we have calculated earlier on, we got our RAW to be 0.03. So this will be VA minus VB equals to 0.03 IS, plus here we shall have RWX. Our RWX was the value we got here, which is 0.015. So here also we shall borrow that value and use it. It is 0.015 times what is in this bracket, which is IS minus 25. So we keep on doing the same for all the remaining values. So moving on, we shall have plus RXW, our RXY, sorry. The RXY value we calculated is that. So we shall have also 0.015 into these values here, which is IS So the value which we have there, which is IS minus 75. Okay? Then we proceed again to the next value, which is plus RYZ. Our RYZ we calculated was 0.03. So it will be plus 0.03 into brackets the value of IS minus 105. Then plus also this one here, which is RZB. Our RZB was also 0.03. So we shall have our 0.03 times the value of IS here, minus 145. So when we come up with that expression, it becomes simpler for us, and therefore we can be able to do what? To get the values that we want to come up with. So you realize that the only unknown we have here is IS, because VA is given and VB is given. Remember from our question, they told us VA was 230 volts and VB was 235 volts. So we shall simply get from here, we shall simply get our 230 minus 235 being equals to, now let us sum all the IS's together. It will be this plus 0.1015 times IS plus 0.015 times IS plus 0.03 times IS plus 0.03 times IS still. So when I feed them into the calculator, I'll have 0.03 plus 0.015, 0.03 plus 0.015 plus 0.015 plus 0.03 plus 0.03. So this is giving me a total of 0.12 IS. So 0.12 IS. Now let us also sum the constants together. For example, I'll have this times this, but they are negatives. All of them are negatives, as you realize. So it will be 0.5 times that, negative, of course, minus this times that, minus this times this, and minus this times that. So altogether, I'm coming up with a 0.015 times 25 plus 0.015 times 75 plus 0.03 times 105 plus 0.03 times 145. So I'm coming up with an answer of negative 9. So simply when I also calculate for this side, I'm getting my 230 minus my 235. It's giving me 230 minus 235, that's a negative 5. Not so? So negative 5, when I take this one this side, it becomes a positive. So 9 minus 5, that is giving me 9 minus 5, that's giving me a 4. So I will have that my 4 is equal to 0.12 IS. Then when I reach that, I can make IS the subject. IS will be equals to 4 divided by 0.12. So when I have 4 divided by 0.12, that is giving me 33.33 recurring. So I'll have that my IS is equals to 33.33 in amps. So, are we together there? see the session is being less interactive. I don't know why. We are still trying to adjust to the new concept. All people are normally silent. Now, that is an interesting question. Now I understand that people are following. So when you look at this diagram that I've drawn earlier on, from that we have assumed to be calculating for current starting from this direction. Now a question will arise, what if I work out from this direction? You will all come up with the same answers, but the way you calculate your current is going to be different. That means for you, your current flowing this direction, let me call it IB, okay? Then when you want the current flowing in this section, all of them will be flowing in this direction like that, okay? Then therefore the current flowing in this section will be IB minus 40. So you get that to be IB minus 40. Then similarly you keep on doing the same thing up to this end, okay? Then even when you're getting your voltage drop, you say VB is equals to the sum of drops along this section plus VA. So you remain with the VB minus VA equals to the sum of the individual drops. But nevertheless, no matter the side you start with, the answer you'll come up with is going to be mathematically the same. It will be identical. So it doesn't matter where you work out coming from, as long as you follow the same principles. The final answer you will come up with is always going to be identical. So looking from that value similarly, I want us to calculate for, now we have the currents flowing in each. We have the current flowing in this section, which is our IS, what we calculated. Allow me to draw something neater. That we can follow. So from this diagram, I'm just going to represent again. So from this diagram that we had earlier on drawn, let me draw something neater so that we can be able to see clearly. We had our loads and we had A and point B. Because you don't have the groups, other groups. Following week after that, you have a test of now you want to present when you have one. So just set your mind, those who present, that day you will present. Those who may not, just again another time. But presentation is there. They will translate for the next thing.
Rejoin.
So you mute. So welcome back from that short commercial break. The announcement is that we are going to do both the what? The test and also the presentation tomorrow. That is the communication from the coordinator. Okay, but it is going to be a hectic day. That is total feeling bad. And it is on Tuesday. So let us proceed from that point. So guys, let us proceed. So we had our currents and we calculated for our current IS to be what? We calculated for the value of IS to be 33.33 amps. So let us substitute for that current in our equations. So for example here, previously, when we refer to the values of currents or the values of the loads that were being tapped off, we had that this was 25, this was 50, this was, hey, the people online can't hear me, sorry. So I was saying that proceeding from there on, we shall have our values of current still that are being tapped off, which was 25, 50, 30 amps, and 40 amps. Then these are our feeders. These are our feeders. Now, let us get the current. We calculated for the value of current IS flowing in the section to be, sorry, not here. We calculated for the value of IS to be equal to 33 amps. So let us substitute for that value here. So from there we have that our current flowing in this section is going to be 33.33. Now similarly, let's get the current flowing here. 33 minus 25 is 8.33. Then similarly, the current flowing here, so it is a negative, so that means it is flowing in this direction, and it is 40.67. And similarly, the current flowing here is 71.67, and finally 111.67. All of them are 0.67, 67, 67. So from there, what do we need to do? We have our points. We have called this W, X, Y, and Z. Now let us find the point of minimum potential just by looking at this. Okay, is this point? The point X is the point of minimum potential because it is where the currents are changing direction. So if the currents are changing direction, that is the point of minimum potential. So The next question here in the in our calculation, the next question here required us to find so currents flowing in the various sections are what we have just found. These values here, these values of 33.3, 8.3, 41.67, 71, and those are the currents flowing in each section. Now, when we look at also the current, when they told us to find the minimum voltage and the point at which it occurs. Now, the point at which it occurs, is this point here where there is change in direction. Then now we need to find the minimum potential is going to be the voltage at point X. So Vx is what we want to find. Okay. So Vx is what we want to find. So now here it is always best for you to choose the direction which won't make you overcalculate. For example, if I'm to work out from this side towards X, I have 3 stages to go through. That is this, this, okay? But when I'm to work out from this direction coming towards X, I have only 2 stages to go through. That is this section and this section. Therefore, I can work out coming from end A towards X, and I will get the same answer as someone who has worked from this end towards X. So to find the voltage at X, when I'm working from this direction, it will be the voltage at W minus the drop between W and X, not so? So Vx by definition is going to be equals to VW minus the voltage drop between W and X. But we don't know VW. So to find also VW will also be equals to the voltage at A minus the drop between A and W. So those 2 stages have given us what we shall need to calculate, what we shall need to use in order to calculate. So let us proceed on and see how this can be got. So for example, VW, to get VW, we have been provided with the voltage at point A, and they gave us the voltage at point A to be 230 volts. So we shall say VW is going to be equals to 230. Now simply voltage drop between A and W. Now simply to get the voltage between A and W is simply going to be the current flowing through that section times the resistance in that section. So calculating for that, we shall have this being equals to minus the current in that section, which we got as this value here of 33.3. So it will be 33.33 times the resistance, which was 0.03. So when we put this into the calculator, what answer do we come up with after subtracting 230 minus that value? 229.001. So we can leave it as 229 just. So we can leave it as 229 volts. Then when we go to find the voltage at point X, it will be VW minus the drop between that. So Vx is going to be equals to our VW, which we have there as 229 minus the drop between W and X, which is the current flowing through W and X, which we got as 8.33, times the resistance across section Wx. Now the resistance across that section is what we had calculated earlier on, which was also 0.015. So this is my times 0.015. So when we put this into the calculator, what answer do we come up with? What answer do we come up with? Sorry? 228.875. So here we are coming up with the voltage being equals to 228.875 volts. And that qualifies to be our minimum voltage across that section. So there we have found it. So that question is done. I think you can see that our answers are ideally the same. So I believe that makes our solution correct. Sorry? I page back a bit. Up or towards my solution. There. Okay. Yes. So, uh-huh. Are we ready to proceed?